Okay, so we've talked about how we have our files, and on a file, you can do a lot of things with a file, but one example of what you can do with a file is you can write code on it. That code will be written in a programming language, which one of the more higher level, sort of more visible aspects of that programming language will be how you write code, or the way you write code. And what I mean by that in this case is that, for example, in C++, you write a semicolon at the end of each of your lines, but in Python you don't. So it's just simple things like the syntax that is determined by our programming language. And then we have discussed how we use a compiler to generate an exe from our programming language, right? We discussed that. And now that we've gotten to that point, let's ask ourselves, how does the operating system choose what code to run? Because we've spoken before, two main parts or two jobs of the operating system we will be discussing is how do we handle what code is run and how do we handle files. Hmm? Okay, so in order to understand that, we have to uh, consult this diagram, right? We have the CPU, we have the RAM, and then in the RAM, a certain section of it is given to the compiler, and then another section is given to a file. Maybe Notepad is open and you're opening a file, right? And then last at the SSD. So obviously the SSD is where we got our file from. We requested it in the previous section, or in a previous section, not the previous section. And now we can interact with our file and play with our file. So our compiler, during the running of the compiler exe, the compiler will read the file, right? It'll read the file and it will determine that it can be executed and it can interact with the file, right? But here's the thing. What happens if we have multiple things running on our computer? How does our computer run multiple things, right? Because, well, our CPU can only run one exe at a time, right? And in order to do that, we need to understand the sort of anatomy, so to say, of one exe, right? Okay, this this is called an address space. Whenever you have a an exe in SSD memory, right? So in disk, and you bring it to RAM. While it is in disk, it is called a program. And once it goes into RAM, because it's being requested by the operating system, and we want to do stuff with it, it becomes a process. Now, processes all have their own address space, and what that means is that they all have their own chunk of the RAM that they can have control over, that they can use to do stuff, right? So in this case, our address space goes from 0 to this FFFFFFF. I don't know if that was right, but it goes to that. And we can see once again that we can see that this is an exe and it doesn't follow our header then content structure, because remember, exe is an exception to that rule in that it has segments, right? We can see we have a code segment, a static data segment, a heap segment, and a stack segment. Now, the data segment is just for data, right? Plain and simple. Code segment is what you will be running, right? Is the stuff that is created. The heap and the stack, though, right? What is the heap and the stack? We've talked about the heap before. Heap before, it is that memory that you have access to and that you can play around with it in way you want, whatever way you want, and then you have to free it as well, right? So you're in control of this memory, assuming you use a language like C, C++, right? Okay. And then what is the stack? The stack is a data structure, right? Is a data structure that is used to store memory, and it is faster than the heap, So you can use it to store like small pieces of memory very, very quick. For example, right here, let's assume this is a little bit of pseudocode, so it's not real code, but it shows us like what code could be. You would add to the stack one, right? So you'd add to the stack a variable, add to the second variable, right? So these would just be regular variables. And notice this structure where you don't remove from the stack as in get me var1, get me var2. You get var2, then var1. This is a LIFO structure. So it has a last in, first out approach. And you can see that here where you just have the opposite of what you put in, right? That's it. The stack and the heap are special pieces of memory that are just efficient or that are used for different purposes. And yeah. Okay, so we understand a process has its own address space with its own sections. Well, how do multiple processes come into play? Well, in order to do that, we have to imagine. We have to imagine first, right? Okay. Well, in order to say what will take over the CPU, right? So we have process one, process two. We have to ask some questions first, right? How long do we want each of the processes to have the CPU, right? Do we want them to first, or do we want them to have equal time? Like, okay, you have 5 seconds, you have 5 seconds, you have 5 seconds, right? Do we want that? Do we want them to be based on which we expect to not require, like I/O, for example, right? Like, files was an example of I/O, but what happens if we need other I/O that we just cannot get, right? Let's assume that we need I/O that we can't get, and that's slow, right? Okay, so for requesting I/O, and we expect a file to require a lot of I/O, do we do we say, okay, run your I/O where you are stalled, you can't do anything, you're waiting on a file, etc. And then we'll have whatever else. And then while we're waiting, we'll run this guy in the background. So do we handle our stuff like that? Do we do we handle it in a way where we say, okay, no, that's do we handle it in a way we say, okay,